help us solve a system of equations. Suppose A is a square n by n matrix, and B is also a square n by n matrix. We call B the inverse of A if A times B is equal to the identity matrix, and BA is also equal to the identity matrix. Matrix B, if it exists, is often denoted as A to the power minus 1. If A inverse exists, then A is called a regular or invertible or a non-singular matrix. If A inverse doesn't exist, then A is typically called singular or non-invertible. We also note that if A inverse exists, it is unique. Here's an example. If we look at the matrices A and B, and we compute A times B, or compute B times A, we end up with a matrix with ones down the main diagonal and zeros everywhere else, an identity matrix. So from this example, we can see that A is B inverse and B is equal to A inverse. The question one might ask is, how can we find the inverse of a matrix? Well, let's start with the definition. For a 2 by 2 square matrix, we define the determinant of A as det A equals A11 times A22 minus A12 times A21. Now, if the determinant of A is not equal to 0, then A inverse always exists. And in fact, for 2 by 2 matrices, the inverse of A is going to be 1 over the determinant of A times the matrix A22 minus A12 minus A21, A11. Here's an example. We want to find the inverse of A. A is equal to the matrix 1, 2, 3, 4. We begin by finding the determinant of A. That's 4 times 1 times 3 times 2 minus 3 times 2. That's equal to negative 2. So using the formula from the previous slide, 1 over the determinant of A times 4, negative 2, negative 3, and 1. Well, since the determinant of A is negative 2, that's equal to negative 1/2 times the matrix 4, negative 2, negative 3, 1. Or simplifying, negative 2, 1, 3/2, negative 1/2. For a matrix A that's m by n, the transpose of a matrix is a matrix B that's n by m, where the entries of B are Bij equals Aji. Essentially, the rows of A become the columns of B. We write A to the power of t to denote the transpose of A. So here are some properties of transposes and inverses. A times A inverse is equal to the identity matrix, and the identity matrix is equal to A inverse A. A the inverse is equal to B inverse times A inverse. We will note that the inverse of a sum, so the inverse of A plus B, is definitely not equal to the inverse of A plus the inverse of B. The transpose of a transpose is equal to the original matrix. The transpose of a sum, that is A plus B transpose, is in fact equal to A transpose plus B transpose. And the product AB transposed is equal to B transpose times A transpose. A matrix A that's of dimension n by n is called symmetric if A is equal to its transpose. Note that only n by n matrices can be symmetric. Generally, an n by n matrix is also called a square matrix because it has the same number of rows and columns. In fact, if A is invertible, then so is A transpose. And the transpose of A inverse is equal to the inverse of A transpose. Now, if we have two symmetric matrices A and B, their sum is always symmetric. However, the same is generally not true for their product. For any n by n matrix A and lambda a scalar, we define lambda A to be a matrix K, where the ijth entry of K is lambda times the ijth entry in A. Multiplying a matrix by a scalar is the same as multiplying each entry by the scalar. So scalar multiplication can be thought of as a way to scale the matrix. Some properties associated with scalar multiplication include associativity. So lambda times psi times matrix C is equal to lambda times psi times C. Lambda times the product of the matrices B and C is equal to lambda B times C. It's also equal to lambda, or B times lambda C, or BC times lambda. The transpose of lambda times C is equal to lambda times the transpose of C. We also have a distributive property. Lambda plus psi times C is equal to lambda C plus psi times C. And lambda times B plus C is equal to lambda B plus lambda C. All this brings us back to the system of linear equations that we were considering earlier. So here we've got a system of linear equations, 2x1 plus 3x2 plus 5x3 equals 1, 4x1 minus 2x2 minus 7x3 equals 8, and 9x1 plus 5x2 minus 3x3 equals 2. If we want to take advantage of matrix multiplication, we can write this as the matrix 2, 3, 5, 4, negative 2, negative 7, 9, 5, negative 3, times the matrix x1, x2, x3, and that matrix product is equal to the vector 1, 8, 2. So in this way, we can represent a system of linear equations as a matrix equation AX equals B. Well, the inverse of a matrix A is A inverse and has the property that A times A inverse is equal to the identity matrix. One way to calculate A inverse, if A is not 2 by 2, then what we can do is we can take matrix A and append the identity matrix to matrix A. This is called matrix augmentation. And then we can perform elementary row operations on the augmented matrix until we have the identity matrix on the left, and the matrix that ends up on the right is the inverse of A. And once we have A inverse, if it exists, we can solve AX equals B by left multiplying by A inverse to get X equals A inverse B. Now again, A here needs to be square and invertible. If A is not square and invertible, we can make some mild assumptions, such as A needs to have linearly independent columns, and we can use the Moore-Penrose pseudo-inverse. Here we take our system of equations AX equals B, multiply both sides on the left by A transpose, and then take the inverse of A transpose A and left multiply again. And so X equals A transpose A inverse times A transpose times B. disadvantage of this approach is that it's computationally difficult. Moreover, for reasons of numerical precision, it's generally not recommended to find the inverse of a matrix or even the pseudo-inverse of a matrix. Gaussian elimination is an intuitive and constructive way to solve a system of linear equations with thousands of variables. However, if the system has millions of variables, Gaussian elimination becomes impractical, as the number of arithmetic operations scales cubically in the number of simultaneous equations. In practice, systems of many linear equations are solved indirectly by secondary iterative methods such as Richardson's method, Jacobi's method, Gauss-Seidel's method, and the successive overrelaxation method. As an example, consider the matrix A, 1, 0, 2, 0, 1, 1, 0, 0, 1, 2, 0, 1, 1, 1, 1, 1. When we augment this matrix with the identity matrix, we get that same matrix with a vertical line and then the 4x4 identity matrix beside it. If we apply Gaussian elimination to this matrix and we take it all the way to reduced row echelon form, we get a matrix that looks like 1, 0, 0, 0, negative 1, 2, 2, 2, 0, 1, 0, 0, 1, negative 1, 2, negative 2, 0, 0, 1, 0, 1, negative 1, 1, negative 1, 0, 0, 0, 1, negative 1, 0, negative 1, 2. The right side of that vertical line is then A inverse. In our next video, we'll talk a little bit more about solving systems of linear equations.